I'll say the full title in the meantime. Towards transparent, richer, and sustainable datasets for code generation model training.
Thank you. That's exactly the keywords. I'm just going to take over and improvise while the tech stuff is being sorted out. So the title is a bit long, but we want to talk to you today about this project, which is a collaboration between our team. So that's Rania, me, my colleague Shihan, who is also in the audience, and also another engineer at RIA, Vincent Sellier. And the whole project is a collaboration between a couple institutions, but we'll get to that later. Real quick about our company. We have two brands. We have Tweak by Modus Create, which is the hat I'm wearing today, although I don't have the actual hat for once. And we have Modus Create. We're basically a consulting company. We do specialized engineering advisory with sort of niche technologies a little bit, but also end-to-end product delivery. And also we sell like sort of Atlassian licenses and stuff. We're a 100% remote company. We're fun. You can join us, or you can also like be a client of ours if you want to. And that's enough for the ads. The project I'm talking to you about, CodeCommons, is built on the Software Heritage project. You might have heard about that. The mission of Software Heritage is to archive and preserve software. The idea is that software is a cultural good, a cultural heritage, such as you know, an old book or a statue, pieces of music that need to be preserved. And if you think about it, software is just ubiquitous in our everyday life, and it's part of our culture. And their mission is really to, well, preserve it for future generations. And that's also why it's supported by the UNESCO, and that's their mission. About the interplay between CodeCommons and Software Heritage. So Software Heritage exists already. It's a giant archive that tries to track all open source code that is in the world. So that's ambitious, and there's a certain lag already. We'll get to that already. And not only snapshots, but all the version history. So if you want to look for some code that disappeared from a forge, like if you remember, for example, I think Bitbucket stopped supporting what was called Mercurial at the time, I think. And you know, those have been archived in Software Heritage, and you can still find the code that was on there on Software Heritage, right? And they store all this. Now, CodeCommons adds a couple components. Most importantly, we look at code not only as the source code itself, but also as what we call contextual metadata. So you can think about, for example, issue descriptions, pull request descriptions, but also for a certain pull request, did a CI run succeed or not, right? All this is important information that can be used for training code generation models such as GitHub Copilot and many others in the meantime. Another component of CodeCommons is enriching metadata. So there are teams in our project that run code analysis, most importantly license detection. One of the goals of the project is to put some ethics and author rights respect back into code generation. So it's a non-trivial task to detect actually the license under which a code has been published. Another task is, for example, language detection. So you might want to check, okay, this is a Python file, but is it Python 3.8, 3.9, 3.12, and so on and so forth. And finally, I talked about authors' rights. The CodeCommons project tries to track precisely the attribution of source code, with the end goal finally being that in a query, eventually a model that supports this can return to the user, okay, this code actually comes from, you know, this original source code file, and the author of this was this and that person, right? And as you know, currently code generation models is a bit the Wild West out there. There's been scandals about big companies basically using a lot of code they technically didn't have the right to, and we want to do much better than that. And now here come to our contributions, which is the infrastructure, the contributions of our company, is the infrastructure. making these data sets filterable, right? So basically, you can run a complex query such as select all code that's implemented in, that runs with Python larger than 3.5, has on GPL or MIT license, and is sufficient or popular, talking about metrics, with say 100 or more GitHub stars, right? Then what you also want to know if you want to do this in a fair manner is where does this code come from? Who has the rights on that? And you would then ask the project, when it's done, find origins that contain code similar to the following code snippet. Then you have a good indication where the large language model actually got its answer from. This graph also shows the contributors to the overall project. So that's Tweak, ourselves, Software Heritage already exists. And then the other parts are done by ARIA and CEA. So it's a collaboration between a couple of big institutions. It's also funded by the French government. Quick couple of words about the Software Heritage data model, because you might now wonder how can you do this? And it's basically what happens in Git, right? So Software Heritage is a giant Git, if you want. We have this Merkle directed acyclic graph, and the idea here is that you look at a source code project in a hierarchic manner. You have nodes such as snapshot, release, revision, a directory. At the end, you have a source code file, which is the leaf node, and each node is labeled with a certain hash. And this hash is computed recursively from the hashes of the children of that node. And eventually, of the leaf node of the source code files, the hashes is just a hash of the file content. With this mechanism, you can define a unique identifier for each object in this source code graph, if you want. And it's called the, it used to be called Software Heritage ID, and now it's called Sweet. What does it stand for again? I did not prepare a joke, so that's a joke now. I think it's Software Hash Identifier.
Not exactly Software Heritage Identifier.
But kind of close. And since April 2025, this is also recognized ISO and IEC standard for uniquely identifying source code. Now, finally, to our contributions, before I'm handing off to my colleague Rania, we are responsible for the infrastructure. In a large sense, what we mean with that is make things work. So we orchestrate an ingestion pipeline on an HPC cluster that is that we have access to by means of this being a government-supported project as well. We develop additional components required during ingestion of new projects, but also synchronization of what we do with the existing Software Heritage archive. And I mentioned a lag earlier. Currently, Software Heritage is lagging behind GitHub by a small number of repositories, which is 150 million. And we want to ingest all those. And this is going to be a first big test of the infrastructure and the pipeline we're building. The graph on the right basically shows all this in context. And if we want to highlight our contributions in the sort of global context here, this would be scalable infrastructure, the big data infrastructure that contains querying tools. And this finally all just allows selection and an extraction of relevant sub-data sets from the overall CodeCommons data set. And with that, I think it's my colleague Rania's turn, who's going to talk about our specific contributions and how we implement those.
Thank you, Simeon. So, in order to ingest this small amount of 150 million repositories, we need the following ingestion pipeline. So this pipeline is composed of 3 backends. So we need a Redis queue in order to record the ingestion task. What's an ingestion task is actually the origins to collect by loader components in our system. We need Kafka journal, of course, to handle the data streams. And we also need an object storage where we store the actual code files. We rely on 3 components: a scheduler and a component, a loader, and a monitoring dashboard. The first component, the scheduler, basically has a list of all the origins that need to be digested. So it writes them down in a Redis queue, and then the loader component picks up tasks from the queue, fetches the origin from the internet, and writes them down into Kafka, into dedicated topics. So we have topics per software heritage object type that were presented in the graph my colleague just presented, like snapshots, releases, revisions, and code contents. And the actual code files are stored, of course, in the object storage. We need a monitoring dashboard that uses Grafana and Prometheus to monitor that the ingestion pipeline is working well. And so we get metrics like the number of origins per second that are being fetched, the size of this data, some CPU, some system metrics like CPU load, like memory load, and so on. So I have to emphasize that Software Heritage Foundation have their own infrastructure, but CodeCommons, since it's financed by the French government and it's a collaboration with a lot of universities, it relies on this fancy HPC called CNES Adastra. Probably some people will recognize it. It's a very powerful environment, but yet very constrained, right? So it's composed of two types of nodes, compute nodes and login nodes, and only login nodes have access to the internet. So we need to be careful on how and where to deploy our different services. Also, we have some limitation about the time. So we cannot submit compute jobs more than 24 hours, and we cannot get allocations that easily. So there's a waiting queue. There's also limited storage quotas for the project, so that we should not exceed, although the people from the CNES HPC are nice enough to grant us some exceptional excess of quotas from time to time. And we have limited software stack, so no Kubernetes, no Docker, no nothing. So we had to have to build this custom orchestration system using simple and efficient Bash scripts. In the previous pipeline I just presented, the services have dependencies between them. So the loader, for instance, depends on Kafka, so it should not be started before the latter is up and running. So for each service we have Bash scripts that start, wait for a service to run, and to stop gracefully a service. We have this global configuration file where we customize our pipeline, set up the environment variables that tell what ports should that service use, where should it be deployed in a compute or in a login node, for instance, how much CPU does it need to be monitored or not, and so on. And the communication between services happens through files, simple and efficient, since they are could be deployed in separate types of nodes, and we have this shared space. So a service just dumps its environment variables that is needed to reach it out by other services. Now that has been said, let's present the actual Python component that we were working on. It's called the deduplicator. So as my colleague said, we are working on this GitLag recovery operation. And when I explained the ingestion pipeline, I stopped at the loader writing objects into Kafka and into the object storage, but I did not mention any graph data. So the deduplicator actually writes down the graph data like in the fancy Merkle graph diagram my colleague showed in ORC format. And it also has a second objective. So, as I said, CodeCommons and Software Heritage have different infrastructures, and we want them to be in sync. So the deduplicator clones data that is present in Software Heritage and exports new data that is meaning possibly the 150 million GitHub repositories back to Software Heritage. To do that, this component relies on indexes. So it has an index to keep track of data that is present in the HPC, an index of data that is present in the Software Heritage Foundation. What's an index? It's a simple key value storage where we track objects with their hashes, like the hash of a content, for instance. And we chose to use RocksDB for efficiency reasons and simplicity reasons. And we have dedicated indexes per object type for snapshots, releases, content, and so on. So how does this component fit into the ingestion pipeline? So basically, the deduplicator uses the Kafka journal, the object storage, and the indexes, the two types of indexes I just mentioned. So once the loader fetches an origin from the internet, writes down the software heritage object into Kafka, the deduplicator consumes the messages from the dedicated topics and then goes to the indexes and checks if they are there. So for software heritage, it checks if the object's hash is within the index. If it's not the case, so it needs to be exported back to software heritage. So, and this is done via ORC format. And even for content files, we just include the content with inside the ORC file, ORC files. Same thing goes for the exporting graph data. So it checks if this has already integrated in the graph data. If it's not the case, it exports it. A brief and a quick view of the architecture of this component. So we have a deduplication manager with a component that is responsible for interacting with Kafka and converting into software heritage formats. We have a graph data exporter responsible for generating the actual graphs. And we have a worker that runs the entire workflow. And you also have an index manager that creates the indexes. So probably you wonder, how do we know what's in software heritage? So we had these exports up to a certain cutoff date of the data present in software heritage, and we use it to build the RocksDB indexes I just mentioned. We have also some utility methods for login and configuration and so on. Working on this was not all fun and games. We had some accidents since we work in an HPC environment. These indexes are kind of have important volumes, up to 1.4 terabytes, and take a lot of time to build, so we cannot afford losing them. And since we are working in a constrained computing environment, we cannot exceed the 24 hours limitation for index initialization job. Due to a bad planning mistake, basically ended up, one of our jobs got abruptly interrupted, and we ended up with a corrupted database. Thankfully, RocksDB provides LDB utility, which is an admin tool, which allows to repair the database. And thankfully, we were able to recover the database. It also allowed us to reduce the size of these indexes, since we have quotas to respect thanks to the compact and the compression utility. Also, we made the most of the HPC thanks to using SSD, since RocksDB is optimized to work on SSD. And thanks to some fine-tuning, we were able to make the use of the compute nodes capacities, for instance, choosing the right memtable size to find the right compromise, not too slow read and writes, and reduce the probability of data loss. And we had to do some Rust coding because some Python methods were not present in the RocksDB libraries, which the libraries that are available are either unmaintained or don't have the methods that we need. So to conclude, CodeCommons is all about, as a reminder, it's all about ethics. The objective is to respect code authors' right? And the second aspect, it's about sovereignty. This data is supposed to be made open source for other people to build their own code generation LLM, and under some certain conditions, of course. And it's all about transparency. The objective is to make code generation reliable. So when you get a piece of code, you are supposed to know why you get it and what's the possible origin of that piece of code. And it's all about sustainability, because eventually this data will be made available, means it does not have to be collected over and over again, which is bad for the environment. As a reminder, the Tweak team contribution, also along with Vincent Sellier from Software Heritage, is about the ingestion pipeline, the deduplicator component. Our next step are pretty easy. Just ingest the 150 million GitHub repositories, develop a querying infrastructure, and create a metadata dashboard. If you are curious, we have some public resources, so don't hesitate to scan the QR code and see what we have been working on. Thank you so much, and don't hesitate to ask questions.
Thank you very much. Any questions in the room?
Yeah, thank you very much for the talk. I think it's a very interesting project. Also, I mean, what is kind of promised in the end with the querying infrastructure and so on, not only for code generation, but also for, I don't know, doing research in how software is developed and so on. I'm a bit curious about how, I mean, who planned this project in this way? I mean, I get the impression that what is actually the problem in Software Heritage that they have this big lag? Because for me, like as a naive outside observer, it seems maybe it would have made sense to fix this problem or scale it up instead of duplicating an ingestion infrastructure and putting it on HPC, which doesn't seem to be the right infrastructure for this kind of job. So I'm just curious on how things came about.
I'll take that one. So Software Heritage has a couple limitations. It's not really meant for large-scale querying and downloading of data, right? The filtering capabilities are very limited, so you can look up, a project by a keyword or by this unique hash identifier, but you cannot narrow it down to a data set that fits your needs, right? So what I showed earlier in my slides were queries such as filter by programming language, by license, by popularity measure, etc. Right? So this is not in Software Heritage yet. And furthermore, the idea of putting, and you're right, it's basically a copy in some sense. By putting this copy on this HPC cluster is that companies and other institutions who want to use that data can get an account on that cluster and basically have access on the same infrastructure to this data set, right? While the Software Heritage archive lives in a cluster that's proprietary, I think, to the CUA. I'm 90% sure, and it's not easily accessible, right? So you can download data from Software Heritage via the API and the website, but it's really not meant for large-scale downloads, and that's why it's duplicated into this HPC cluster. And you might also wonder why HPC. It's not very compute-heavy for now, but what we definitely need is the storage, right? So we're talking Software Heritage alone is 2.5 petabytes of data compressed. And now imagine all the lag catch-up plus future projects. And this amount of storage is most easily available in these scientific compute clusters.
Any questions?
Thank you for the talk. Just out of pure curiosity, how much time would it take to ingest 150 million GitHub repositories?
Very good question. For now, we are benchmarking the ingestion pipeline to actually make that estimation and make sure that's fast enough. So I don't have the exact answer for that question. But don't hesitate to contact us later, because we'll have it soon, I guess.
Yeah, so we're really expecting, I think, somewhere in the range of maybe a couple months, right? And while this is hopefully an async task, we can continue on the querying infrastructure, for example.
Anyone else in the room? Yeah.
Is there a plan to make it as easy accessible as with GitHub? Because with GitHub, it's very simple to find an author, all the repos they contributed to. Is it just some sort of cold storage, or will there be a plan to make it very easy browsable?
I can take it if you're okay. So it's meant to be for institutional clients, like not really individuals such as you and me, but really for, say, companies who want to develop a new large language model, for research institutions that do a research project. And the way to access it will be really getting an account on the scientific compute cluster. So it's a bit cumbersome. It's not as easy as just going on a website and doing a query and downloading it. And it's also impractical, right? Because the amount of data is insane. You would probably want to download. And the use case are really institutional users mostly.
Still on the Software Heritage website currently, like they have this browsing interface where it's easier to use than going to do the cluster. But as Simeon said, like it's for another type of users.
Yeah, and eventually, basically, all the data we ingest onto the cluster will be copied back, at least the source code contents, into the Software Heritage archive, right? So ultimately, this will be up to date, and you can use the easy interface on Software Heritage without the additional benefits of the CodeCommons project, which are tied, of course, to the infrastructure as well.
Thanks for the talk. I actually went on, and probably a follow-up to the previous question, I went on Software Heritage to try and query the existing code that you've ingested. I noticed that at the moment, you're able to query via the UI, either based on the hash identifier or keywords. I know in your slides, you kind of showed a prompt that was like, find like a nice query that was sort of like user-friendly. Is that already implemented, or is it planned to be supported, like a query based on natural language, or like, let's say, I'd like to look for software that's sustainability related that helps compute my scope 1 emissions, for example. I don't know, something around that.
That's actually the ultimate goal of CodeCommons. So the objective of CodeCommons is to integrate this enriched metadata to make querying code easier. So that's actually in our next steps, the querying infrastructure. So to be able to query maybe in a human readable format the system, and filter like based on programming language, design patterns, some quality metrics and so on. So that's the ultimate goal.
We are late, I apologize, but please continue the conversation
Yes,
offline. Thank you again. Let's thank our speakers and we'll move on to the next talk. Thank you.